What is up, chumps? Today we are going to be learning about peer-to-peer networks. What they are, why they're important, and what they do for us, specifically in blockchains or distributed ledgers. So let's just jump right into a little graphic I've set up for us. It's incredibly good looking, I know. Let's make it bigger. There we go. All right, so starting off, a peer-to-peer network, as it is stated, is a network that is created by different entities that are talking directly to each other, as opposed to through some centralized service, like a website normally is, where you host it on Amazon or AWS or Azure, and you're speaking with their servers to receive information about the website. Let's say, for example, as well, like the domain name services that exist. Those are also centralized services. And peer-to-peer networks are set up, or can be set up, so that people can communicate without relying on any of these centralized services. And the peer-to-peer networks are set up and they are highly redundant, so that even if an individual, what's called a node, goes down, the network can still function without that node, which is a complete, the centralized services on the opposite end, they need to create their own redundancy, and commonly they still struggle to do this. And so if like AWS goes down, a lot of the internet actually crashes. And we've experienced this quite a bit in recent years, where most of the internet just crashes and burns because something happened at Amazon. So peer-to-peer networks are incredibly powerful because they allow you to transmit messages and to communicate without needing the centralized service. And specifically in blockchain or in distributed ledgers, they're incredibly powerful because they allow people to cooperate without, or to join the network and to contribute to the network and participate in, whether that be validation or storage of information, or CPU power. There we go. There's lots of distributed networks that you can create using peer-to-peer networks. And each peer-to-peer network has pros and cons, or I shouldn't say pros and cons, there's different strengths or purposes, right? But they all function at the foundation in pretty much the same way. And that way is by keeping track of their buddies, their best friends. So that's what this here is for. So Bob is aware of George. And you can see that George is also aware of Bob. And peer-to-peer networks are created or set up as a graph structure. A graph is defined by, you have nodes, which are these circles, and then you have connectors or references to other nodes in the graph. And these are called edges in a graph. So Bob and George have a reference to each other, and they are aware that they exist in this peer-to-peer network. So let's say if I have Alice over here, let's say that George is aware of Alice. We gotta make it blue. So let's say that George is aware of Alice, but that Alice is not aware. Let's see if I set this to default style. Boom. So George is aware of Alice, but Bob is not aware of Alice, and Alice is also not aware of George. But let's say that Alice is aware of Bob. So we still have this graph structure, and we still have nodes, and every node in the graph is connected to another in some way, shape, or form. This is called connectedness within a graph. And in a peer-to-peer network, especially on a distributed network, you want to have connectedness, full connectedness throughout the entire peer-to-peer network. These are mathematical terms, by the way. So when I say that in a graph you have nodes and edges, a graph is made up of nodes and edges. And edges can be directional or bidirectional. So this is an example of a bidirectional edge, and I should probably actually just give this an arrow on each side so it's a bit more clear. So Bob is aware of George, and George is aware of Bob. They send messages to each other. Alice is aware of Bob and will send messages to Bob. George is aware of Alice and will send messages to Alice. And so this is a connected graph. In a peer-to-peer network, you don't ever want to have just a random person sitting out here. Let's just say Carol is sitting out here and she isn't aware of anybody, and no one is aware of her. She's not part of the graph. And so in a peer-to-peer network, she is effectively useless because she isn't aware of anybody in the graph, and so she can't contribute to the network in any way. So let's say that Carol has just spun up her node and is trying to connect it with the peer-to-peer network that exists. She would need to have at least one reference or one, I guess, URL to one of these other nodes, to Bob, George, or Alice, in order to connect to and link up with the peer-to-peer network. Once she links up to one person, she can ask Bob, like let's say she links up with Bob, and she's like, hey Bob, please give me all the people that you are aware of. And so Bob sends back information, and perhaps in that transaction or that request, Bob also adds Carol as a node that he's aware of. So now we've got a bidirectional reference to Carol here. And Bob responds and says, hey, yeah, I'm aware of George. And so Carol's like, oh, great, another person. And so now Carol is now aware of George, and you can effectively traverse a graph in this way by asking peers who they're aware of, and you can get all of the nodes that exist in the ecosystem. There are mathematical ways of doing this, depth first search versus breadth first search. There are like Dijkstra's algorithm. There's lots of ways to traverse a graph effectively. I'm not going to get into that. Just know that you can. And that being able to do so is very important. So that's how a peer-to-peer network roughly functions. Or how you add a new node to the peer-to-peer network. I'm going to delete this. Doesn't look good. You add a new node to the peer-to-peer network, how a node finds other nodes, how they can query for each other and just kind of find additional people, and that you want to create connectedness within the peer-to-peer network and not have these disconnected, or what's called actually disjoint, portions of the graph. Otherwise, you run into issues. Let's talk about that just a little bit actually. Let's say that I have Carol 2. I don't know, coming up with names. We'll call this Alpha. Let's say that we have Alpha, we have Omega over here. The first and the last. And let's say that they aren't aware of anybody else in this network. These guys, like, being completely honest, these guys are disjoint. They're separated from everybody else. Messages that are sent to them only get transferred between these two. And this is an issue because, let's say, the network itself is run over here. I mean, this would be akin to a hard fork in the network, where these guys decided, you know what, I'm not going to talk with any of these other people. I'm going to specifically remove them. They upgraded their node version, and I didn't want to do that. I didn't want to follow that. I felt that, like, the owners, let's say, of Alpha and Omega decided that, hey, we want to create Bitcoin Cash. We want to decrease the block size from 10 minutes to 5 minutes, or from 10 minutes to 1 minute, so we can handle more transactions. And so they created a hard fork for Bitcoin Cash that changed and altered how the nodes communicated and the block speed. And so they had to create this separate, completely separate network. So these nodes can't communicate to these ones. And just to show that that's the case, I'm going to change the color real quick to red. And so these guys communicate and store references to each other in a different way. So that's what like a disjoint graph would look like in this context. In a peer-to-peer network for a blockchain or a distributed ledger, you would have a hard fork that is created by this, or by doing this. So that's a graph made up of peers. How and why do I care about this? The why is very simple. The peer-to-peer network is used to transmit your messages across or to whoever needs to receive it. In a distributed ledger, you generally need to commit transactions to the network. And in order to do that, you send your transaction, structured properly, however the protocol expects it, to one of these nodes. So let's say that I, Sterling Long, I'm going to change the color of this here circle to be a nice, is that salmon? Periwinkle? To a nice periwinkle, and I'm going to say, this is Sterling. This is me. And I'm sending a transaction to this network. I'm going to send it, and I'm going to send it to Bob. And the goal of the peer-to-peer network is to effectively transmit and gossip about my transaction with everybody in the network. And so when I send my transaction to Bob, Bob's immediate response is to take that transaction and do a couple of things with it. First and foremost, he's going to begin validating that transaction. And the validation process is dependent on the consensus mechanism that the ecosystem has, whether it's proof of work or proof of stake or something in the middle, permissionless, permissioned. There's lots of different consensus mechanisms. I'm not going to get into those, but essentially Bob is going to be validating my transaction. That's step one. Step two is he needs to let everyone else in the network know about the transaction. And so Bob gets all of his best buds. He's like, I've got references to my two best buds, Carol and George. And I'm going to tell them about my transaction that I just received from Sterling. I've done a rough validation. I've validated. I personally have the entire blockchain available to me, the entire state. And so the references that Sterling sent to me and the signature that he sent to me, those are valid. And so I trust this. I'm going to send it off. I'm going to gossip it throughout the entire network. So Bob is going to take my transaction that he received and just validate it. Like I say validate in the sense here where it's a rough validation. He took the state of the ledger that he is aware of, that Bob is aware of, and validated my transaction with it. Now these other people, they might have a different current state. So like if Bob is nefarious and I'm nefarious and we're trying to transmit a nefarious transaction that double spends or something like that, these other nodes, when they receive that transaction, will compare the validated transaction with theirs, and they will also validate it and be like, this doesn't match up. It's not good enough. And they would reject it. So while Bob is okay with this, Carol, George, and Alice likely are not. Now keep in mind this, due to the different consensus mechanisms, there's different ways to validate. So I'll dive into and kind of look at a different proof of work and proof of stake at a very high level in just a bit here. But continuing on with the gossip, so Bob has gossiped my transaction. Oops. Oh, alright, that doesn't work. Bob. So Bob has gossiped my transaction to Carol and George. George do the exact same thing. They gossip the transaction to all of their peers. So George is aware of Carol. Carol is aware of George. And so George is going to send this transaction and gossip it to each other. They'd be like, oh, I already got this. I don't need to really do all that much with it, for example. Alice is going to receive it from George, and then Alice is going to send it back to Bob, and Bob's going to be like, yeah, okay, I already got this. We're good to go. So in that way, your message that you send to one person in the network is transmitted throughout the entire graph using this gossip mechanism. A healthy network will gossip and transmit a transaction throughout the entire network incredibly fast. That's its goal, is to get the transaction to all of the nodes as fast as possible so that they can be validated. The goal is to validate your transaction as fast as possible while still maintaining decentralization and security. So a really good network with really good protocols and solid memory management will be able to send and gossip your transaction throughout the entire network very, very fast. Very fast. Especially if transactions are small. So that's how transactions are propagated throughout the entire network and how they're gossiped. Bob tells his best buds, George tells his best buds, and eventually everybody knows about it. Except for the people over here, Alpha and Omega, because, I mean, they're off on their own, doing their own thing. We don't care about them. Oop. So, my transaction has been propagated throughout the entire network. Now, every single node has the task of officially committing it to the ledger. And I'm going to cover the two main ways that this happens. First way is proof of work. The second way is proof of stake. So in a proof of work network, we have these other, you could call them nodes in the graph, but they're specialized. And these are your miners. So when a node receives a transaction, it will transmit the transaction to the miners that it's aware of. And the miner's job is to put the transactions into a block and then begin creating the cryptographic proof of work for that block. That's effectively what a miner is supposed to do, right? Once it's created the cryptographic proof of work, it sends that information back to, I'm going to change the color of this guy as well, be yellow. Once it has received or found the cryptographic proof of work by hashing the block data repeatedly until it finds a set number of zeros, right? And if you want to learn more about that, I have a video specifically on hash functions and how they apply in proof of work. I'll have the link in the video below. But once the miner has found the cryptographic proof of work, it sends the block back with that data to the node Bob, and Bob's like, hey, this checks out. I'm going to propagate that, the block, throughout the entire network. And so it follows the exact same pattern of when I sent my transaction to everybody. Bob, Carol, George, and then Alice all receive this block, and they say, yeah, this checks out. I like this. And so they'll add the block to the chain that they currently have. They'll update their state with that chain. Or with the new block, sorry. And that's how a block is effectively committed to the blockchain. Now, miners might find blocks at differing times, and so multiple miners could solve a block at the same time with different values. But consensus is achieved just by choosing the longest chain. Whichever chain ends up being the longest is the chain with the most amount of work behind it, validating the transactions that took place there. Which is why you have, if 51% of the nodes are working, or miners are honest, you are over the long term, you are going to be okay. There can't be a double spend attack, because eventually you will have, the 51% will have the longest chain, which secures the network. In a proof of stake environment, these nodes are likely also the validators. And so when I send a transaction to Bob, he will validate the transaction with with his current state. Be like, yes, this checks out. It's good to go. I can validate this transaction with my current state. It's not double spending. It's not disobeying the rules of the protocol. I can attach my signature as a validator to the transaction, and then I can propagate that transaction throughout the entire network as well. Again, following the exact same paradigm. I find my peers, I tell them all about the transaction, I send my signature along with it, and eventually everybody knows about it, and if enough of the validators approve my transaction and essentially add their signature to it, it gets committed to the distributed ledger. So speaking a bit towards proof of work and proof of stake, there are novel mechanisms coming out to make proof of work and proof of stake more scalable. Cadena is one of the blockchains that has created a sharded proof of work, so that you can effectively have multiple blockchains side by side and add more blockchains as the needs of the protocol and the network and the ecosystem grows. This is very powerful and is amazing actually as far as scaling up proof of work. In proof of stake, there are also novel mechanisms coming out that have to do with memory management. And when I receive a transaction, what part of the ledger is it affecting? And let's lock down that portion of the ledger and allow other transactions to still be committed while I'm executing this potentially more complex transaction. And SWI Global and Radix DLT are two blockchains. I shouldn't call them blockchains. They're two distributed ledgers that are really pushing that forward. Those two are proof of stake. So Cadena, Radix, and SWI are three distributed ledgers with really, really novel consensus mechanisms that allow them to scale while still maintaining security and decentralization. From my point of view, they've solved a great deal of the blockchain trilemma. So that's proof of work, proof of stake, and roughly how it works in my peer-to-peer network. So once those transactions have been validated and committed to the ledger, I receive I'm able to query and be like, has my transaction finished yet? Or the protocol might emit some kind of event that I'm able to listen to and effectively say, tell me when my transaction is committed to the ledger. And once it's committed to the ledger, I can respond to that. And that's what your DApp would do. So Sterling, you could replace Sterling here with a DApp that has committed or sent a transaction to the peer-to-peer network that is the blockchain or distributed ledger. The distributed ledger propagates the transaction throughout the entire ecosystem. It validates the transaction, whether that be through proof of work or proof of stake. Once it's been validated and committed to the ledger, I receive a response back saying my transaction succeeded. So that is a peer-to-peer network. That's how they work. That's why you care. You care because it allows us to avoid the centralized services that exist and create decentralized ecosystems that can function without needing any middleman, without needing any middle party to run them, to make them work. This is going to become increasingly important, I feel, as centralized ecosystems, social media, and things like this become more and more biased or in some way towards individuals. So the power of these peer-to-peer networks that are run by the community, by the world, and just by any random Joe sitting in his basement cannot be overstated. They are powerful. They are incredibly useful. And they are the foundation of every decentralized ecosystem in existence. Pretty cool stuff, right? I hope you've enjoyed this. If you have, please smash that subscribe button. I'm here to teach. I'm here to help people learn and grow. I really want you to know how the technology that you interact with on a daily basis works. And not just visuals like this. I also love to get into the code and walk you through code. Because I feel like a lot of people, code is scary, right? But if you have someone there to walk you through just line by line and you can see it and read it and I can describe to you how it works, there's a lot of power in that. And there's a lot of learning that can happen when you yourself can read code. So I'm here to teach, I'm here to help you grow, and I'm here to challenge you to be more connected with the technology that is around you. And I don't say connected in the way of I'm looking at social media all day. I mean connected in that you know how it works. And you can describe that to someone else. There is so much power in that. And being honest, you'll feel like the coolest person in the room if someone is like, what the fetch is Bitcoin? And you can be like, well, let me tell you. So, smash that subscribe button. I would love to see you again. I'm here to serve. Have a wonderful day. Also, my wife said actually, it is Valentine's Day, so happy Valentine's. If you're watching this and it's not Valentine's Day, happy Valentine's Day. And have a wonderful